Okay, video started, so don't talk. Oh, do we have a lot of good stuff. Okay, I got one more lesson. I can't believe I forgot this one. I already turned it on. Remember I told you everybody should have this box at home, and whenever you're shopping and spending money, and they always ask this question, do you want a receipt? And the answer should always be yes. Yes, stop it. Who said no? Yes, the answer should always be yes, always. You put that receipt in a box. Well, sure enough, I get an email last night, I responded this morning, from a company who I shipped a generator to. You guys know what I'm talking about? Big, it's a portable generator, backup generator, because I have a sump pump in my basement, and when the electricity goes out, my basement will flood if I don't have this hooked up to a generator. Well, this generator is under warranty, and so I had to send it back. I sent it back, but they said, we're not sending you a new one until you prove that you sent it back. Luckily, when they said, do you want a receipt? I said yes. Found the receipt in the box, which was hard because what month is it? October? So I have 10 months of piles of receipts in this box, and I throw them in there, so I'm picking out receipts, trying to find it, took a picture of it, and my new generator's on its way. All because, now listen, I could have figured out a way around this, right, without having that box of receipts. But I want to tell you, this is at least the third time this year that having that box of receipts made things happen fast and easy. That's the advantage of keeping your receipts. 3 different times this has happened where I had to go through there, grab it, and it just made life a lot easier by having that piece of paper proving what I had to prove. So there's the lesson again. Keep your receipts. Yes, you want a receipt? Yes. Take it out of your pocket or wherever you keep it and put it in a box, and at the end of the year, switch boxes. All right, so there's the life lesson. Let's get to the new stuff. Let's start with, you got something different this week. You got 2 homework assignments, both a written and an Excel, and there's Excel problems expected on the written. This Excel is so special that you are handing in the Excel spreadsheet itself. Do it on that spreadsheet. Use that spreadsheet. If you change the name, put your name in the title of the spreadsheet. Matter of fact, let's look at it. I'm going to go over in detail this spreadsheet on Thursday, but right now it says DS302 Fall 24 Week 8 Excel assignment or something like that. Just add your name into the title of it when you send it to me. It makes it a lot easier in case whatever. When I download it, it makes it so easy for me to find it because sometimes I don't download it in the right place. But you're going to be making a couple of tables, and you're placing your tables right on the sheet. You can place them right on the front, or you can go to a new sheet, and then you got to answer these 2 questions at the bottom. I am going to show you in detail how to do this Excel on Thursday. Let's look at the written. You have a written assignment also, which includes some Excel equations. Is this it right here? Yeah, this is it. You have, it's just one problem, but you have to do it 2 different ways. Don't forget, this week's all about T. There's Z last week and T this week, because this week we have sample standard deviations or sample variances. Again, don't let those intermixing words fool you. The variance is just the standard deviation squared. The standard deviation is the variance square rooted. They're the same number. But this time, we have to distinguish, all right, we're reading a problem, is it Z or T? Okay, it's T, but is it assumed equal variances? Is somewhere in there, does it say, okay, we have sample 1 and sample 2 standard deviation of variances, but is the words telling us anything about the population variances? If you see the words assumed that the population variances or standard deviations are equal, this is the formulas you're using. This is your test statistic formula. This is your confidence interval formula. But you're saying, oh, this problem's giving me the sample standard deviations of variances, so it's a T, but somewhere in there it does not state, let me repeat this, nowhere in there does it state that the population variances are assumed equal. It won't literally reach out at you every time and say they're not equal, but you got to recognize it's not telling you they are equal. And if it does not tell you they're equal, you got to use these equations, meaning they're not assumed equal. This is your test statistic equation. This is your confidence interval equation. And the biggest difference between both of these is how you calculate the standard deviation. That's the biggest difference. Now I want to review something real quick. I want to make sure we're all on the same page. So all of this between quiz 2 and quiz 3, by the way, what we learned last week right before quiz 2, you may have noticed quiz 2 didn't have any problems related to that lecture. There'll be a problem related to that lecture on quiz 3. All right, just so you know, I got a heads up on that one. We're right now, right here, independent population, independent samples. We're going to be learning related populations, related samples, and proportions, and we may even go into population variances, maybe. But right now, we're right here. But there's 3 different types of calculations just in this box alone. There's Z, and then there's 2 different T calculations based on whether the population variances are assumed equal or not. So look at these 3 again. Here's all 3 of them. The first one that we learned last week is that the population standard deviations or variances are known, that it's being given to us. These 2 down here, the population standard deviations are not being given to us. The sample standard deviations or variances are being given to us. And then we got to figure out if the population ones, if anywhere does it say they're assumed equal or not. So before I go into these formulas, I want to read a couple of problems. I got them all lined up here. And I want you to tell me Z or T. All right? According to a what does that say? Health of Boston report. According to a Health of Boston report, I gotta look down here. Female residents in Boston have a higher average life expectancy as compared to male residents, according to the Boston Globe. You collect the following sample data to verify the results of the report. You also use a historical population standard deviation of 8.2 for females and 8.6 for males. Z or T? Why? You hear her? She knew it was Z because in that that last sentence, it was giving you the population standard deviations. That's how you knew it was Z. And we're using last week's formulas. Let's go to the next one. Yeah, see which one's next. Here we go. A chartered financial analyst CFA designation is fast becoming a requirement for serious investment professionals. It is an attractive alternative to getting an MBA for students wanting a career in investments. A student of finance is curious to know if a CFA designation is more lucrative option than an MBA. He collects data on 38 recent CFAs with a mean salary of $138,000 and a standard deviation of $34,000. A mean of 80 MBAs result in a mean of $130,000 salary and a standard deviation of $46,000. Excuse me. Z or T? Z or T? Z or T? Z, because you're given the population standard deviation? It's T. You're given the sample. Let me read it again. This sentence right here. It says he collects data from 38 recent CFAs with a mean salary of 138 and a standard deviation of 34,000. You're given the sample mean and standard deviation in one sentence, and they're both related to the sample. So it's not the population standard deviation, it's the sample one. That's why this is T. But now we know it's T. That's this week. We got to say to ourselves, anywhere in there does it mention that the population variances are equal, assumed equal? We're just equal. We learned it last week. Specify the hypothesis to test whether the CFA designation is more lucrative than the MBA. One tail or two tail? Wow, you guys, is anybody here? We are recording. One tail or two tail? One. One tail, that's right, because it says more lucrative. It doesn't say equal, doesn't say different, it says more lucrative. Here we go. Calculate the p-value and calculate the value of the test statistic and p-value. Do not assume that the population variances are equal. There's the sentence you were looking for. You know now it's not these two equations, because it doesn't say they're assumed equal. It says assume they're not equal. It's these two equations now. Here's your test statistic. Here's your confidence interval. Now, we got to get another step farther. On the next test, there's an extra step that you have to answer it's gonna be very much like quiz 2, but this extra step at the end. You're now not gonna be telling me just whether you're rejecting the null hypothesis or not rejecting the null hypothesis, but what that means. What that means. So it's gonna be specific in the directions, and we're gonna talk about more between now and the third quiz, but I need you to add words. The null hypothesis, we reject the null hypothesis, and then you need to add a sentence what it means. So I want to use this one as an example, the CFA thing. As I'm reading it, I want you to say to yourself, if we were rejecting the null hypothesis, what does it mean? What would be true? All right? A chartered financial analyst, CFA designation, is fast becoming a requirement for serious investment professionals. It is an attractive alternative to getting an MBA for students wanting a career in investing. A student of finance is curious to know if the CFA designation is a more lucrative option than the MBA. I'm going to stop right there. All right, my null hypothesis, H sub O, H sub A is the alternative. The mean, and the mean, 1 minus mean 2, minus mean 2. We know this part. This is where we're at. Now, from that sentence I just read, one of them is going to be less than, one of them is going to be greater than, and then whatever the equal goes with is going to be in the null hypothesis. Here is the sentence. If it, here we go. A student of finance is curious to know if a CFA designation is more lucrative option than the MBA. So the first sample is coming from CFAs, the second sample is coming from MBAs. And we're trying to test if one's more lucrative than the other, that makes it one tail, and we're putting in the alternative what it is we're trying to prove, that one is more lucrative than the other. If what we're trying to prove is true, CFAs would be more lucrative, meaning higher annual salary, than MBAs. So if I subtract the two, the first mean would be CFAs with the higher salary minus the MBA means with the lower salary mean. Would I be less than, greater than, or equal to 0? Did anybody hear that? In the alternative hypothesis, what would go there? Less than, greater than? In the alternative hypothesis, we're trying to prove greater than. Because if the first one's going to be greater, the CFAs is going to be greater in salary than the MBAs. Let's say it's 138,000 versus 130,000, we're going to have a positive number. So this is going to be greater than 0. This one is less than equal to 0. There it is. Now, think about this. We just came to the end of this problem, and we just rejected the null hypothesis. We rejected the null hypothesis. We rejected that. So we found evidence of what? What did we find evidence of? You got to turn this into words. We just did all the math, and we're saying we're rejecting the null hypothesis. We're rejecting that one mean minus the other mean is less than or equal to 0. We found out that one mean minus the other mean is greater than 0. That's the one that we're saying is true. The other one's rejected. What does it mean in words?
That the CFA was more lucrative than
Everybody hear this?
MBA?
Yes.
The,
Yeah. Extra credit. Oh, I'm sorry.
Oh, right.
But damn, you deserve it. CFA's designation incomes are significantly larger than MBA's if we were rejecting this. That's what we found out to be true. That CFA's, if we were rejecting it. Now, if we did this whole problem, we come to find out that it's not, we can't reject it. So then the words would be, we cannot reject the null hypothesis, therefore CFA designation mean income is, we do not have evidence that it's larger or greater than MBA yearly income. That it's not, that we don't have evidence that it's more lucrative. So either we have evidence that that what we're trying to prove is true, or we don't. All right, let's do another one. We're not going to make it through everything today, but whatever we don't do, we're going to put it on Thursday, because Thursday's lecture was kind of short anyway. And that way we won't have a big long in class. Instead, we'll have a normal in class, right? Oh, did you see what just happened?
What page was that on?
That was on page 354. Page 354. Now we're doing number 12. Okay, here we go. An entrepreneur owns some land and he wishes to develop. He identifies two development options: build condominiums or build apartment buildings. Accordingly, he reviews public records and derives the following summary measures concerning annual profitability based on a random sample of 30 for each such local business venture. For the analysis, he uses historical population standard deviation of 22,500 for condos and $20,000 for apartments. A or Z? I heard it over here.
Z.
I heard it, that's right, Z. Those words right there, that he uses a historical population standard deviation was the key words that tell you it's a Z. And the whole Z calculation from last week, from last Tuesday. Let's do one more. Oh, wait, let's take this a step farther. Let me read it again. Accordingly, what I'm about to ask you is this a one tail or two tails? So I'm gonna read the sentence again. He identifies two development options. Accordingly, he reviews the public records, the following measurements based on, what is he trying to do? Owns some land. He identifies two development condominiums or build apartment buildings. Accordingly, he reviews the public records, derives the following summary measurements, annual profitability based on a random sample. Again, so it's gotta be down here further. Here's the question. Set up the hypothesis to test whether the mean of profitability differs between the condominiums and apartments. One tail or two tail? Two tail, differs. There's the key word right there that tells you it's two tail. Either they're equal or they're not equal to. They're equal or not equal to what number would be in the hypothesis?
Third.
Say it again.
Third.
No. Say it over here. Any of these, when there's two means involved, every one of the hypotheses have what in there for a number?
Zero.
Zero.
Yeah.
Zero. All of them have zero for these two different. They're all going to either be less than equal to zero, greater than equal to zero, or equal to zero for the null hypothesis. Zero is the number. When we're doing these confidence intervals, and this is why I'm glad the cameras weren't rolling. Even though on page, you gotta find it, 322 of your book, it says that the confidence interval method is for two tail. I've read all over the internet because I kept questioning myself. That doesn't seem right. That we can use confidence intervals for one tails. So we're gonna start using confidence intervals for one tails also, and it's the same thing. Does the hypothesis number fit in the confidence interval? If it doesn't fit, you reject. If it does fit, you can't reject. So we're changing that rule. And I apologize for my mistake, but I got it off of page 322. Says confidence intervals are for the two tail. Anyway, so one more. We're gonna read one more, and you tell me if it's Z or T. David Aronson has been working as a lecturer for Michigan State University. What a coincidence. There's no way this book's from Michigan either. The last 3 years. He teaches 2 large sections of introductory accounting every semester. While he uses the same lecture notes for both sections, his students in the first section outperform the students in the second section. You guys barely outperformed the other section, by the way, on that quiz. Barely, just by a teeny bit. You had 3 100s where they only had 1 100. I think that's what made the difference. He believes the students in the first section not only tend to get higher scores, they also tend to have lower variability in scores. David decides to carry out a formal test to validate his hunch regarding the difference in average scores. Random sample of 18 students in the first section, he computes a mean and standard deviation of 77.4 and 10.8 respectively. The second section had a random sample of 14 students with a mean score of 74.1, standard deviation of 12.2. Z or T? T. We just got given the sample standard deviations. That's how we know it's T. Now let's keep reading to determine, are we doing this equation assumed equal or not assumed equal this equation? Remember, if you know this is a T, and it doesn't mention anywhere they're assumed equal in the population, you assume they're not equal. Let me repeat that. It doesn't always tell you, when you see a problem that's giving you the sample standard deviations, it doesn't always come right out and tell you, by the way, the population variances or standard deviations are assumed not equal. It won't necessarily say that. But anytime you're supposed to assume they are equal, it always tells you. Everybody hear that? It always tells you. So you know to use this formula if you go, oh, it's T, I have the sample standard deviations, and it's telling me that the population standard deviations are assumed equal, so I'm using these formulas. Or you're looking at a problem, you're going, oh, I've got the sample standard deviation, so I know it's a T, and there's nothing in there about the population standard deviations being equal, so it must be this formula. That's the assumption you gotta make. How crazy is that? So, in this case, you said it's a T, but we have to figure out whether we're using assumed equal or not assumed equal formula. Construct a null and alternative hypothesis to test David's hunch. Nowhere in there does it tell us anything about the population standard deviations being equal. You guys agree? And so we would then go with this formula right here to get our test statistic or our confidence interval, whichever way we're going. All right, let's get into it. Now that we see what we're doing, here it is formally. Where's the first formula? Again, here's the first one. This is where, hang on. There's the first formula, that's this one right here. I want you to recognize something in this formula. Look at what I did. I cut out this part right here because we know this is 0. So I just condensed it and just put this, because this is all 0 for this class. Always 0 for this class. Here's what's different. Let me read this out loud. Ready? It's the sample mean number 1 minus the sample mean number 2 in the numerator. In the denominator, on the right side, it's 1 over sample size from the sample size of number 1 sample, plus 1 over the sample size of number 2. When you add those together, you gotta multiply them by what's called a pooled variance. There's the weird part. But it's a real easy calculation, and it's right here. The pooled variance takes, now I wanna make sure you understand what each of these variables are, so I wrote them in yours. This big S with the square is the variance for number 1. This big S with the square with the number 2 below is the variance for number 2. This N1 is sample size 1, and N2 is sample size 2. So all you gotta do is take sample size 1 minus 1 times the variance for 1, add it to sample size number 2 not minus 1 times the variance for number 2. Don't square anything, that just represents variance. Variance over sample size 1 minus 1 plus sample size number 2 minus 1. That's called the pooled variance, and that's that number in the denominator. Go ahead, Nina.
Can you write it down like when we receive it? Because it's confusing.
Well, and not right this second, that'll take forever to write down. But I'll tell you what I'll do, I'll write it out and I'll put it here on Thursday. All right? Everybody see what's happening now? This is your pooled variance. That's that number right there. And then after you multiply that, you gotta square root the whole thing before you divide it into the numerator. You gotta square root this whole thing. If you're doing confidence interval, it's the very similar formula, but you gotta have that critical T based on the significance or confidence, whatever's given to you. The sample mean 1 minus the sample mean 2 plus and minus the critical T, there's that same denominator. 1 over sample size 1 plus 1 over sample size 2 added together times that pooled variance, square root the whole thing. This is your error, your standard error. Add the critical T, this is your margin of error. And then add the 2 subtracted, plus and minus, now you have your confidence interval. Good, Mark.
What is N2? N2.
Oh,
What is
N2 is sample size 2.
Oh, the sample size too?
Yeah, sample size 1 is N1, N2 is sample size 2. Good.
So, where it says where T has N1 plus N2 minus 2, and then degrees of freedom?
Yeah, that was my next thing. The degrees of freedom for this T, don't forget, this is degrees of freedom for assumed equal. So I'll put it here. Degrees of freedom, that's just for this one. Because you just have to add both sample size. So what is it, N1 plus N2? N1 plus N2 minus 2. You add both sample sizes and then subtract 2. That's your degrees of freedom. Add both sample sizes, subtract 2. Right? We're about to do a problem so you can see all this in action. You can see say it again. This degrees of freedom for this one, hang on a minute. We're not there yet, but I just want you to look at it. Hang on. That's the degrees of freedom formula for this one. Since you asked. Everybody hear me? I don't know if we'll get that far today, but it is on the plan today. This is the big difference between these. Now I want to tell you something. You have to do this on your homework.
What is that?
This is the degrees of freedom calculation for that if they're not, if you're doing T
I'm scared.
and they're assumed not equal. Now here it is in words, ready? The variance from the first sample over the number in the first sample. The variance in the second sample over the sample size, number in the sample for the second sample. Add them together, square the whole thing. There's your numerator. Denominator, ready? Variance from the first sample over the sample size from the first sample, squared. Then divide that by the sample size from the first sample minus 1. Then over here, the variance from the second sample divided by the sample size from the second sample, squared, divided by the second sample size minus 1. Then you add the left and the right, then divide that into the numerator. Now I'm not done. No matter what this turns out to, you round down. Oh my God, did I just say that out loud? Oh my God, did you hear that? No matter what this turns out to, you round down. What if this came out to 17.92? What is our degrees of freedom? 17, you get it. You round down to a solid number like 17.
Just for the not assuming
Just for the what? No, just for this. Degrees of freedom over here are easy. You add how many in the first sample plus how many in the second sample, subtract 2. Degrees of freedom are easy. That's the big difference with this one. Degrees of freedom are going to take time. So on that written assignment, it's asked you to do it twice. It's asked you to do it assuming the population standard deviations are equal. Then it's asked you to do it again, assuming the population standard deviations are not equal. And one of your first calculations is this when it's not equal. Because you got to get the degrees of freedom to be able to do this, or to do the critical approach at all.
Do we need degrees of freedom to do the actual, like, problem?
To do what?
Problem?
Like you don't, if you're doing P, well, no matter what, you need degrees of freedom. You can't get your P value, you can't get your critical value, you've got to have that degrees of freedom. Yeah, because even the confidence interval approach uses the critical T, so you got to have degrees of freedom. All three approaches. Yeah, well, this is the how to get your critical. Oh, I'm sorry, you're right. Critical. And these different bits. Hang on. She's asking you how to get your critical. We're going to do it just like we've always done it, which is equals T critical. I, N, V. I gotta look at my directions. I don't have it memorized. Comma. I can't write in there. Depends whether it's one tail or two tail. And this is degrees of freedom here. Does that sound right? I gotta look at my notes. I don't have these memorized. Okay, P value is going to be equals, I gotta remember, hang on, T, D, I, S, T. That first number depends on whether it's one tail or two tail, but then you have your degrees of freedom, comma, and then you gotta tell if it's one tail or two tail. Or is this having, which one do you have to put a 1 or a 2 on the end? I don't have them memorized.
Where's our little cheat notes?
There we go, hang on, here's my cheat notes. Okay, this one you have to put 1 or 2 tail, parentheses. And then what is that first number? Depends on whether it's a 1 tail or 2 tail. Over here, depends if it's a 1 tail or a 2 tail, what that first number is. These are the exact same formulas we've been using all semester. And once you get this test statistic or you get degrees of freedom, depending on which one you're doing, you plug them into the same formulas we've been using. All right, let's keep going through this example. I think it will help.
What formula is that?
This one or this one? This is critical value. This one's P value. Huh?
Can you write that?
This one is critical value.
Thank you.
Critical value right there, and this one is p-value. Is that what you said? Right there? Okay. Critical value, p-value. Yeah, once, this is gonna be your test statistic T here, and then this is gonna be your upper and lower interval, same with this. It's just how you get to that test statistic is different. That's all that's different. And then what degree of freedom you put in here is different, depending on which one you're doing.
So do you round down for both degrees?
No, there is no rounding here, because you're just subtracting 2. But here is the only one you round down for, just this one here. The degrees of freedom, when you're doing T, and the population variances are not assumed equal, that is that degree of freedom that you're rounding down. You ready for an example? Let's do it. Whoops, we gotta find it.
Is that the same formula for everything else? Like the one tail is double the significance, and then the two tail is that's the same?
Same, yeah. She's asking if this is the same. Right here, ready? I got it on my notes. If it's one tail, that should be double the significance. If it's two tail, that should be only the significance alone, without doubling. Down here on this T distribution, if it's a one tail, oh no, we're putting in the T stat. Oh, we're just dropping the negative, that's all. Right there is gonna be the T stat, the test statistic. Test stat goes there. Right there, test. But drop the negative. Test stat, drop negative. Drop negative symbol. There you go. Only if it's negative, you drop the negative symbol. Say it again. Point right here. If you put a dot, then you can leave the negative symbol, but you don't do the one tail, two tail. I can't remember what the rest of it is. I can't remember. I'm so used to using this one, I can't remember the rules on all of it. Okay, here's our example. Okay, go ahead, Mom. Those are the Excels. This one's defined critical value, and that one's defined. But it's the same Excels we used for the all semester. Yeah, for either one of these, what has changed is how you get to these numbers, but this has not changed at all. This stays just like it has been. Just the manual changes, just the manual part changes. Here's our example now. You ready? You are a financial analyst for a brokerage firm, and there are differences in is there a difference in dividend yields between stocks listed on the New York Stock Exchange or the NASDAQ Exchange? You collect the following data. Now look at this data. New York Stock Exchange, sample size 21, sample mean 3.27, sample standard deviation 1.3. NASDAQ, sample size 25, sample mean 2.53, sample standard deviation 1.16. Zero T. Zero T.
Oh,
Well, I was here, the only one answering. Zero T.
T.
Stop it.
T.
T. T. It literally says sample standard deviation 1.3, the other one's 1.16. There's T. We got that far, right? Now let's keep reading. Assuming both populations are approximately normal with equal variances, do you hear that sentence? Am I doing this formula number 1 or this formula number 2? Number 2, because right there it tells us assume equal variances in the population. So now we know what formula we're using. And then it says, is there a difference between the average yields of these two exchanges, stock exchanges, at 5% significance? One tail or two tail? Very good. Did you hear her? She said two tail. Because right there it says, is there a difference? It doesn't say one's more than the other or one's less than the other. It says, is there a difference? That means the two samples subtracted would be 0 or not equal to 0. Now we're going to calculate our T statistic. Notice the part I leave off is a 0. And you can just take it out of there. Look at the pooled variance. Look at the pooled variance. Sample size 21 minus 1 times standard deviation of the sample squared. We had to turn it into a variance. 1.3 squared. Here, sample size number 2, 25 minus 1. The standard deviation of the second sample, we had to square it to turn it into a variance. Divided by 21 minus 1, 25 minus 1, add those two together. 1.5021 is our pooled variance. That's that number right there. This is just like you're doing part A of your homework. To get to that number right there. Now you plug that in here, 1 over the sample size of number 1 is 21, 1 over the sample size of number 2, 25. The first mean was 3.27, the second one was 2.53. That's the yield, 3.27%, 2.53%, I believe, are the yields. And there's our 1.5021 we calculated here. We do all the math on that, look at our test statistic T. That's where we're at right now, right there. 2.040, okay? Let's get our p-value. Help me out. Right here, here's the formula for p-value, equals T, D, I, S, T, parentheses. What's that number? 2.040, comma, what's the next number?
44.
Ah, how do you know it's 44?
21 plus
21 plus 25 minus 2. Very good. Extra credit?
Yeah.
You can have yours.
Oh.
What was it? I already forgot.
21 plus 20.
What is it?
5 minus 2.
40 what?
21 plus 25 minus 2.
44. Comma, and then is this a one tail or two tail? You told me. Thank you. There it is. What does that equal? Do I have it on my piece of paper, or did I already, do I need to do it? Blah, 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 blah. It equals 2.5, oh, wait. I don't have it.
2.0154.
This equals. No, that can't be right. 2 point something can't be right. Come on, anybody have this? What is it? What is, he's right? 2 point something? Oh, 0.047, is that what you said?
Yeah.
0.047, that's not what he said. All right, reject or not reject? Wait, what's going on? How did we get this on the screen? Hang on, let me get this back up here. Hang on, reject or not reject? Our p-value is 0.047. Our significance is what? 5. Do we reject or not reject?
Reject because.
Well, hang on. You guys got answers coming from all over the place, and they're not the same answer. Is our significance higher or lower than, is our p-value higher or lower than significance? Lower. Anytime your p-value is lower than your significance, you must
Reject.
reject. Reject. Anytime your p-value is less than your significance, you reject. Let's see what, I don't think they use p-value. Instead, they said, let's find our critical value. Oh, let's find the critical value. Here we go. Equals T-I-N-V. This is a two-tail, so we put the significance in, which is 0.05, comma, degrees of freedom, we said was 44. And this equals 2.0154. There's our critical value. Where am I at? I'm right here. Right there, I'm showing you how we got this critical value, 2.0154, by using that TIMV formula. There it is, right there. Now, our test statistic, where is it? 2.040 has to be compared to that. They're darn close to each other. Look at the line here. There's 2.0154. There's 2.040. My question is our test statistic inside, closer to 0, or outside our critical value? Outside, which gives us evidence to reject or not reject? Reject. Anytime your test statistic is outside that critical value, you reject. Notice, this is all that's changed, but once we got over here, it's all the same that we've been doing.
So you drew the arrow to TIMV for the first one. It's still the same thing, one tail, double significance, two tail, significance.
Right, and because it's two tail, I put in 05. Hang on, I gotta read my cheat sheet, I gotta remember now. Double the significance if it's one tail, only use the significance if it's two tail. I put in 05. If it were a one tail, I would have had to take that up to 10.10. There was another question, go ahead.
The degree of freedom is the same for both the
No, degrees of freedom that we just did, which we added the two sample sizes and subtract two, is only for this one. The degrees of freedom for this one is that huge long formula. Dude, that huge long formula. I wanna make sure you know that formula, right here. That's degrees of freedom for the second one. We haven't done this confidence interval yet, no. But let's talk about what would be the numbers used here. Ready? What would be this number? Wait, let me bring, oh, everything's right here almost. So what would be this number right here? 3.27, exactly. This would be then the other mean, 2.53. This critical T would be what number? 2.0154, right there, times, where's that pooled variance? There it is, 1.5021, times 1 over sample size number 1, which is 21, plus 1 over sample size number 2, which is 25. We do all that math, times the critical T, we add it to the 2 subtracted, we subtract it to 2 subtracted, we get our upper interval, we get our lower interval, and then what is it we will look to compare these intervals to? What will we compare the intervals to? Not the test statistic, not the critical value. The hypothesized mean, which is 0. We're looking to see if 0 fits between the upper and lower. If the 0 is between the two numbers, do we reject or not reject? If 0 is between the upper and lower, we not reject. If 0 is not between the two numbers, then we reject. Look at you guys, we've never gone this late, have we? Oh, I thought it was 3:16. The pooled variance, here we go. There's the pooled variance calculation. Right there, the pooled variance calculation. Here's the example. Oh my God, this is getting to be too much, isn't it? Man, we just aced that second quiz and now look what's happening. By the way, you know the third quiz has got to be harder than the second quiz. We got to get back in. No, we don't have to, but there's too many students not getting challenged when we have.
That's not true.
Look, when we have an average that high, I got to make sure everybody feels challenged.
Well, I felt challenged.
So you want us to fail?
I want you to feel challenged. How are we doing? Let me look at my notes. Okay, now this is the other test statistic formula if we find that the population variances are not equal. I summarized it here. Sample mean 1 minus sample mean 2 over variance of 1 over the sample size 1 plus variance 2 over the sample size 2, square root. This is pretty easy because there's no pooled variance. This is easy. But to have to do that degrees of freedom calculation is much harder. That calculation then is the part you gotta have, that degrees of freedom, to be able to do either one of these, p-value or critical value approach, but you gotta have the critical value to even do the confidence interval approach, so no matter what, you gotta calculate that degrees of freedom. On homework problem, the written part of your homework, B, that is what you're showing me. That is the hard part about B. The hard part about part A of your homework is you gotta do that pooled variance. That's the hard part of B, is that pooled variance, or A, I mean. And part B of your homework is doing this degrees of freedom. So that you can, once you get this test statistic, you can do any of these.
On the homework, is it one of each or just one?
Yes, one of each. Ready? Whoop, hang on. There's the homework, and all it has is an A and B. And A says, do your calculations using the p-value approach, assuming that the standard deviations of the population are equal. B says, do all your calculations doing what approach here? Also p-value approach, what a mistake that was. But assuming the population value, variances are not equal. this one. So that's the only difference between them is one of them you're doing it like this, and B you're doing it like this with the same numbers to see how different the results are. All right, but that's it for today. Let's stop there. That's enough. That's enough. We'll pick up from here on Thursday. Thanks for showing up. I'm glad I held your quizzes so you came.